Have you ever wondered what makes your smartphone smart? Or how your car knows the perfect engine timing? What about the magic inside your laptop, your TV, even your coffee maker? The answer is smaller than a fingernail, yet holds the power to run our entire modern world. We're talking about microchips, the brains of every electronic device you own. Today, we're going on an incredible journey to uncover the secrets of how these tiny marvels are made. It's a process so precise, so complex, it's like building a skyscraper on a grain of sand. So, stick around, because you're about to see how we turn simple sand into the super-powered heart of technology. It all starts with something surprisingly common: sand. But not just any sand. We need extremely pure quartz sand, which is rich in silicon dioxide. This sand is melted down in a furnace at scorching temperatures, over 2,500 degrees Fahrenheit, to create a pool of 99.9999999% pure molten silicon. This level of purity is absolutely critical. Even the tiniest impurity, like one foreign atom in a billion silicon atoms, can ruin the final product. From this molten silicon, we grow a massive single crystal called an ingot. A tiny seed crystal is dipped into the molten pool and then slowly, very slowly, pulled upwards while rotating. As it rises, the silicon cools and crystallizes around the seed, forming a perfect cylindrical ingot that can be over 6 feet long and weigh hundreds of pounds. This process is so delicate it can take days to complete. The result is a flawless single crystal structure, the perfect foundation for our microchips. Once the ingot is fully grown and cooled, it's time for slicing. Imagine a giant, high-tech deli slicer, but instead of meat. It's slicing one of the hardest materials on Earth. The ingot is cut into ultra-thin, perfectly flat discs using diamond-tipped saws. These discs are called wafers. Each wafer is then polished to a mirror-like finish, so smooth that if you expanded it to the size of a city, the biggest bump would be less than an inch high. These gleaming wafers, typically about 12 inches in diameter, will become the canvas for hundreds, sometimes thousands, of individual chips. Now, the real magic begins. Photolithography. This is the heart of chip manufacturing, where we print the intricate circuit patterns onto the wafer. First, the wafer is coated with a light-sensitive material called photoresist. Think of it like the emulsion on photographic film. Then, a machine called a stepper or scanner projects a pattern of ultraviolet light onto the wafer through a template called a mask or reticle. This mask contains the blueprint for one layer of the chip's circuitry. The light changes the chemical properties of the photoresist it touches. After the light exposure, the wafer is bathed in a developer solution. Depending on the type of photoresist used, either the exposed or unexposed areas will wash away, leaving a stencil of the circuit pattern on the wafer surface. This process is repeated dozens, sometimes over 100 times, for each wafer. Each time, a new layer with a different pattern is added, building up the complex, three-dimensional structure of the transistors and circuits. It's like printing a book, but instead of words, we're printing billions of microscopic switches, layer by layer. With the photoresist stencil in place, we can now permanently alter the silicon wafer itself. One key process is called etching. This is where we use powerful gases or chemicals to carve away the parts of the silicon layer that are not protected by the photoresist. It's like a microscopic sandblaster, creating the tiny trenches and pathways that will form the chip's wiring. The precision required here is mind-boggling. We're etching features that are thousands of times thinner than a human hair. Next up is deposition and doping. Deposition is the process of adding thin films of different materials, like copper for wiring or silicon nitride for insulation, onto the wafer. This is often done through a process called sputtering or chemical vapor depositions, where atoms of the material are basically sprayed onto the wafer, creating a perfectly uniform layer. Doping is another critical step. This is where we intentionally introduce specific impurities, like phosphorus or boron, into the silicon crystal. This changes silicon's electrical properties, allowing it to act as a semiconductor, a material that can be switched between conducting and insulating electricity. This on-off switching ability is the fundamental principle behind every transistor, and therefore, all of digital computing. This cycle of lithography, etching, and deposition is repeated over and over, building the chip from the ground up. It's an incredibly complex dance of light, chemicals, and physics. To give you a sense of scale, a modern high-end processor can have over 50 billion transistors packed onto a chip the size of your thumbnail. Each one of those transistors is built through this multi-layer process. The entire manufacturing process happens in what are called clean rooms. These are some of the cleanest places on Earth. Thousands of times cleaner than a hospital operating room. A single speck of dust is like a giant boulder that could land on the chip's circuitry and destroy it. That's why workers wear those iconic head-to-toe bunny suits to prevent any contamination. After weeks of processing and building up all the layers, the wafer is finally complete. But it's not a single chip yet. It's a platter holding hundreds of them. The next step is testing. A machine with microscopic probes touches down on each individual chip, or die, on the wafer. It runs a series of electrical tests to see if the circuits work correctly. Any die that fails the test is marked. Given the complexity, it's normal for some of the dies to have defects. The percentage of good chips on a wafer is called the yield, and it's a key metric for manufacturers. Once the testing is done, the wafer is ready to be diced. A precision diamond saw cuts along the grid lines, separating the wafer into hundreds of individual dies. The good dies that pass the test move on, while the bad ones are discarded. Now we have our raw, naked chips. But they're incredibly fragile and need protection to be useful in the real world. This brings us to the final stage, packaging. Each good die is carefully placed into a protective housing, usually made of ceramic or plastic. This package does three things. It protects the delicate silicon from physical damage and the environment. It provides the electrical connections, those metal pins or balls you see on the bottom of a chip that allow it to connect to a circuit board. And it helps dissipate the heat generated by the chip during operation. Tiny gold or copper wires, thinner than a human hair, are bonded from the die to the external pins of the package. Finally, the package is sealed and the chip is tested one last time to ensure everything is working perfectly. And there you have it. From a humble grain of sand to a polished ingot, a patterned wafer, a tested die. And finally, a packaged microchip ready to power our digital lives. It's one of the most complex and precise manufacturing processes ever devised by humanity. The next time you pick up your phone or turn on your computer, take a moment to appreciate the incredible journey of the tiny silicon heart beating inside. It's a true testament to human ingenuity. Thank you so much for joining me on this deep dive into the world of semiconductors. If you found this fascinating, please hit that like button and subscribe for more explorations into the technology that shapes our world. Let me know in the comments what other tech you'd like to see explained. Until next time, stay curious.